Good. So graphs and trees are easily like one of my favorite topics in all of computing. They're so interesting. They're so important. Some of the most interesting algorithms are the algorithms that you do on graphs and trees. They solve so many of the most important problems that we have. So I think about like Google Maps, and I think about all of the graph theory that is going on behind the scenes, and even just on a basic level that, like, you know, you've got a map, which is a type of graph, and Google is so efficient at finding a route between 2 points that could be clear across the country. And it blows my mind because you think about all of the different nodes and edges between here. So this is one of my favorite topics, and it's also a topic that you could spend like months and months and months on. So my intention here is to go kind of give an overview and talk about some of the most important algorithms. Be some time for questions. We'll talk about how graphs and trees are represented, a couple common applications, and kind of go from there. So give me feedback as we go, what, you know, if this is making sense, if speed up, slow down, that sort of thing. So the first thing that I thought was kind of funny, I put out this survey, is like, what do you want to talk about in data structures? And like half the people were like trees, and the other half were graphs. And I kind of chuckled because they're kind of the same. The tree is a type of graph. Which like when you kind of zoom out, so a graph and a tree is really just a connection of nodes and edges. And that's the kind of important thing to wrap your mind around, is like, whatever we're doing, we've got nodes and relationships between those nodes. So some examples, and I'll put this up for folks to see here at least. So lots of examples. Your dependency tree, when you install some NPM packages, there is a tree of dependencies that node or NPM manages, so that you make sure you get not only the package that you want, but the other packages that package depends on, and the other packages that those packages depend on, and that you're not kind of installing packages ad infinitum, you know? In JavaScript objects have a tree-like or even graph-like quality to them, because you have an object which relates to parent object or kind of prototype. You can have relationships between objects. File system is a perfect example of a tree. Facebook graph, so basically like the data that is Facebook, the relationships between nodes, which would be people, and edges, which are the relationships. You know, there's like all of these interesting questions about, if you have two people in this graph, how do you find the mutual friends? And how do you find the shortest path between them? Because there are probably lots of paths, you know, 6 degrees of separation, but how do you find the shortest path between them? Maps, like Google Maps. Parsers, so the parser that is parsing your JavaScript under the hood is usually implemented in some sort of tree. And then, of course, internet routing is a big graph problem. You know, how do you find the shortest route between, you know, a server in New York and a computer in Oakland, California? So this is the kind of stuff that we're talking about. And even though graphs themselves like are kind of, there's kind of a basicness to them, they do end up solving or modeling some of the most important things that we do. So the difference between graphs and trees is that trees usually have a root node. That would be like the top. If you imagine a tree, we usually we usually draw trees like this, where there's a node and then some edges, a node, and more nodes on edges, right? And in this example, this would be the root. And there's kind of there's like a parent-child relationship, which is typical in trees. And so like a parent directory, a subdirectory, or child directory. And then trees cannot contain cycles. So you can't have something that goes like this and then something that goes like that, because that would be a cycle. Graphs, on the other hand, it's kind of the wild, wild west. You can have nodes, you can have edges, they can be connected, they can have cycles, they cannot have cycles. That about does it with the like fundamental differences. You know, trees are uniquely suited to some types of problems that, and kind of graphs other types of problems. Trees are kind of I think the easier thing to start with. So I want to talk about a couple different kinds of trees. So there's something called a binary tree, and this is an example of a binary tree, meaning that every node can have up to 2 child nodes. You know, oftentimes you'd call this left and right. So we've got binary trees. You could have a tree that had, you know, 3 or 4 child nodes, and it just would not be a binary tree. Within the kind of set of binary trees, you can actually have something called a binary search tree. And I mention this because this shows up sometimes in algorithm challenges, and just it's one of those things that's useful to know. So a binary search tree is, oh, and I should say, when it comes to graphs and trees, nodes can have, you know, children, but they can also have a value. Oftentimes with graphs, you can also have the edges have a value. So like if you've got, you know, Oakland and Berkeley and San Francisco, you can have edges between them that represent, say, the distance between them. And that's how you would, if you were calculating the shortest path between 2 points, you would need to look at the length of those edges to know what the shortest path was.
So you can have that with both trees and
yeah, I was trying to think of an example of a tree where an edge would have a length or would have a value, and I couldn't think of anything, but that doesn't mean there's not one. In many of the kind of common tree examples, it's the nodes that have a value. And so in the case of a binary search tree, the nodes have values. And in particular, there's an ordering to the values. So you might have a tree that has 1, and this is 3, 4, hope I do this right, 7, 9, 10. So binary search trees, the kind of technical definition is that all left descendants, so all left, yeah, we'll say descendants, are less than or equal to the node in question, which is less than, so it's less than or equal to the node in question, which is less than all the right descendants. And I don't think that's actually a word, but we'll go with it. Right descendants. So let's see if that's true here. So 7, all of these descendants should be less than 7, and they are. All of these should be greater. And it has to hold for each node. So here, the left descendant is less than that, the right descendant is more. So it's called a binary search tree because this particular ordering makes it very conducive to a quick search. You can find an item in this tree in log n, big O of log n, and that can be really useful. you can actually think about this. Have you ever played the game where it's like guess a number, like somebody picks a number between 0 and 100, and then the other person has to guess what that number is, and each time you guess, the person will say higher or lower. So that's a kind of like fun childhood example of the log n time complexity of getting to the answer. That you don't actually have to say, is it 1? No. Is it 2? No. Is it 3? No. You can say, okay, well, if we've got 0 to 100, I'm going to pick 50. And then if I know that it's greater than 50, it wasn't 50, but it's greater than 50, then I'll say, okay, I'll pick 75. Okay? Well, it's less than 75, so I go between those two. Okay, how about 60, whatever, 63 or something. So by doing that, you're actually kind of modeling a binary search tree. You can imagine a binary search tree where all the numbers from 0 to 100 were in it, and you're just traversing down the tree each time getting the information, is it greater than or less than that? And so it's possible in that game, I forget what the actual relationship is, but it's possible in that game to guess the person's number in log n, where n is the number of items. Making sense so far? Yeah.
And then so does that logic applies to all of the nodes, or just like only applies to the direct child nodes?
It applies to all nodes.
All nodes.
So it has to hold for all nodes in the tree that their left descendants are less than or equal to n, which are less than right descendants.
So, like for example, if number 4 instead of 4 is 8, would that apply here because 8 is larger than 3?
Say it again.
Sorry, instead of 4, if we put 8,
okay,
would that still apply because 8 is larger than 3, and then 1 is smaller than 3? Would that apply, or we have to also check in with the 7 as well?
What do folks think?
I think you have to check in with the 7 because it says left descendants all of the D. So it means not only the immediate descendants, but all of the descendants.
Yep.
So all the descendants, not just the immediate ones.
Yes. So this is an invalid binary search tree because you look at the left descendants, 8 is greater than 7, so it doesn't work. So the 8, where would we put the 8?
It has to be on the left side of the 9.
Yeah. And then it works. Yeah, so that's a binary tree and then a binary search tree. And a binary tree is just each node has up to 2 children. There are a couple of terms that are used, and there are actually a lot of terms that are used to describe trees and graphs. And I'll give you just 2 that you may find come up. One is balanced. So what do you think a balanced tree means? What do you think it means if we say a tree is balanced?
We have the same amount, equal number of nodes on the left and to the right.
Yeah, very close. So it's equal number of nodes on the left to the right. The caveat is it can differ by 1. And that's because, say it was balanced on the left and the right, and then you added a node to the tree, there would be no way to balance that tree,
Sure.
in that case. So we make this, we make the definition that it can vary by at most 1. So I'll just write that up here. Balanced. Oh, that's. So left and right have, how do I say this? Have the same number of nodes plus or minus 1. Can differ by. Can differ by at most less than or equal to 1 node. The other one that may actually come up if you end up with a algorithm challenge that's tree-based is complete. Who wants to take a stab at complete?
We would include all the numbers. 2 is missing from that graph, so maybe it's incomplete.
Okay, it's a good guess. Not right.
Maybe it means that every node has 2 children.
Okay, also close. Not quite there.
Does that mean that the value on the left equals the values on the right?
So that would be balanced, right? The number of nodes on the left is almost 1 different from the number of nodes on the right.
Sorry, but I meant like the value of the nodes, like in terms of numbers right now. So.
Oh, so like the sum of, okay, interesting. It's also not that. So you think about it again, when I think of the word complete, I kind of imagine a tree that's like, you know, this. So we've got this kind of like uniform tree, right? And say this is 4, right? So 2 children, 2 children, 2 children. It's kind of even looking. Except then we have to account for Foday's, you know, what we were talking about with Foday, which is what if there aren't that many nodes in the tree? Can it still be complete? Yes, it can, but it has to be filled left to right. So this is also complete because it's as filled as it can be. It's as complete as it can be. And the same is true for, let me think for a second. Yeah, I think the same is still true for this. Because you read it basically like row by row, left to right. So filled, 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 not filled, not filled. So this is still complete. And so, you know, this will become more relevant when you get into the actual algorithms that you do to look through trees and the kinds of problems that you solve with trees. But kind of mark it in your brain. It's a good thing to clarify with an interviewer if you're getting a question about this, whether the tree that they're giving you is balanced and or complete. What would the definition of complete be? Did I write this down? Every level is filled left to right, except possibly the last one. Every level filled left to right, except possibly the last. Make sense? Yeah.
So when you had a node under 9 before, you said also it's a complete one, or is it not complete?
So like this
Was this complete?
what do we think? Is this complete?
That's complete. Slice and
So we can fill in as many as we can. It'd be nice to put an extra one on the right of that line, then it would really let. But because we don't have one to put there, this is as good as we can do. We did it left to right, so complex.
Yep. Every level is filled left to right, except possibly the last. So this row is filled left to right, this row is filled left to right, this row is filled left to right, except possibly this last row is not completely filled.
Except possibly the last. Okay, that makes sense.
it's kind of like the exception of the balance. That one exception, right?
Yeah.
Justin,
Yes.
if you were missing a left node, like that child of 3, that would make this tree incomplete.
So missing which one? This one, the 3?
The number 1, the child of 3, number 1, yeah. If you were missing that, and
Yeah.
that
So
would be.
I think if we were missing that one,
So this is incomplete.
incomplete.
Because now we have 2 rows that are not filled, right?
Well, because it's on the left. Like the idea is complete every level filled left to right. So the minute we can't fill that first on the left, it's already incomplete.
Oh, okay. Even if it's only the last one?
Mm-hmm.
Even, okay. Oh, I see.
Because it's left to right and all the rows except the last one.
Got it.
Is this balanced?
Oh. It might be.
I would say yes.
Different by less than 1 node, right?
What do we think? Is this tree balanced? Getting a gentle head nod from Jack. Look at.
I think it is balanced.
Yeah, look at the definition. The left and the right subtrees can differ by at most 1 node, and they don't even differ by 1 node. They are, they both have 2 nodes in their left and right subtrees.
So is the reason why this is incomplete also is because it's assuming that we haven't adequately searched through all the values? Because if we can't fill it in, that means we haven't been able to do. Does that make sense? In other words, like if I don't have a node at the leftmost side, that means something incomplete happened with the search of values or something, or the input of values. I don't know.
There's no
I-
search for just.
That would be the rearrangement of the tree, right?
Right. Yeah. So I think I get what you're onto. So the question is like, well, I guess the thing that I would kind of put back to the group, and then we'll see if we can wrap around to what you were saying is there a way that this collection of nodes could be a complete binary search tree?
Yes.
How would it look?
Just by adding 1 node to the left side of 3.
Okay, so we could add 1 node to the left side of 3. If we used only these nodes, only these 5 nodes.
Oh, just shift the.
Yeah, shift the 4 to the left side.
Delete 4.
Oh,
We'd
wait,
have to
but you
rearrange
can't.
the whole thing.
Right.
So how would we rearrange it?
Well, wouldn't we make 3 the root node somehow?
Okay, so if you made, so I'll do it over here. 3 is the root node.
Then all of a sudden now we have. Oh no.
Yeah, you can see right away that
Yeah.
the only, there would be nothing off to the left.
That's right. It would be. Oh, then make 9 the root node because you have everything.
Okay, so if we make 9 the root
If
node,
anyone have it on the right.
Yeah, it's well. The completeness is left to right anyway.
Oh, that's
Right. So I don't know.
So,
okay, but 9 is the root node. I'm with you. What goes over here?
And then let's do 7.
Okay, 7 goes over here.
And then we can do 4. Then we can do 3 and 9.
Where do they go?
So 3 is going to be on the left, and 9 on the right. And now we can do 4 on the. We can do 4 on the left of 9.
Well, why are we repeating 9 though?
Yeah.
Do we? Oh.
Yeah.
Oh, did you mean 8?
8? Yeah.
Yeah.
Okay.
Is this complete?
No, because the first one, the second row is also.
Actually, it might be complete but not balanced.
I think it's not complete because complete says every level can go left to right. If you look at the first level down, it's not.
Oh yeah, you haven't filled 3.
You haven't filled this node spot. Whatever the value would be, this is missing, therefore it's not complete.
Got it. Okay.
Because this row has, this node, so it has to fill left to right, and we filled left to down.
Got it.
And that's basically because it's unbound.
That's why it's unbalanced.
That's
Yeah.
what I was thinking.
Yep, that's why it's unbalanced. So who wants to take another hack at it? How can we turn this into a complete binary search tree?
Maybe make 4 the root.
Do we have to use all the nodes?
Yeah.
Yep, all 5 nodes.
7 on the left.
7 on the left, 9 on the right.
And then 7 on the left.
Then it would be 3 on the left, right?
Oh yeah, sorry.
Or
Yeah,
Why don't
3
we
on the
make
left.
7?
But
If you change
Four.
7 to a 4.
Yeah.
Yeah.
Okay.
Yeah,
Seven
that's,
on the
yeah.
right.
7 to a 4, and then
7 off.
Yep. There we go. Now we have a complete tree.
huzzah! You didn't have the same reaction I did. I was like, so binary search trees, pretty good.
That was cool.
I did say that I would try to take a picture of stuff before I erased it.
So is that all, that is specifically a binary search tree, or is that just a tree? Should be those rules?
It is a tree. It is also a binary tree, and it is a binary search tree. And the binary search tree, again, is, it meets this condition that all the left descendants are less than or equal to any node,
Right.
less than or equal to, or less than the right descendants. It's also a complete binary search tree. So this is a fine binary search tree. It's just not complete. And because it's not complete, we lose the guarantee that we can do a search in log n time complexity, big O of log n.
So a binary tree by itself is just nodes that have 2 things.
Yep.
Okay. Okay.
Pretty cool.
Very cool.
So there's something else called a min heap.
What?
A min heap. Min for minimum. Anyone have an idea of what that would be?
No.
So a min heap is a complete binary tree. Complete. And binary meaning it has up to 2 nodes, 2 children. Where each node is smaller than its children.
Both children?
Mm-hmm.
So it's like reverse.
Not even reversed. It's kind of like, if you can think of it, it's kind of like rotated almost.
Oh.
So, and I don't promise that I won't screw up here. So if we had 1, and then I'm making this way too big. So 1, and then over here, we've got 2 and 4, and then over here we've got 9 and 13 and 17. Does that work? Each node is smaller than its children. This is smaller than both its children. This is smaller than its children. This is smaller than all its children.
And again, not only the immediate children, whole thing, right?
Right.
Okay.
Is there some rhyme or reason to how it's supposed to be distributed for normalcy?
It needs to be complete.
Okay.
So that's it's filled left to right in all the rows except possibly the last. Could we have this, 13 and 9?
I was just going to ask that.
That's what I don't know.
I think it can because the condition you mentioned, the only condition you mentioned is that the node is smaller than the children node. So my guessing, if that's the only condition you mentioned, it's complete, and in this case, the node is smaller than the children.
Mm-hmm.
So is that correct?
I'm like 92% confident, yes. part of my asking that question is I was asking it to myself, does this work? Yeah, and I think it does. What can you imagine the value of a min heap is?
You mean like one of the applications of it?
Yeah, why have a min heap? What's it good for?
It's easy to find maxing.
It's easy to find the minimum. Why does that matter?
Because you don't have to traverse the whole tree.
You don't have to traverse the whole tree. if you have a situation where you consistently need to know the minimum of a set of elements, this turns out to be a very good data structure.
Is there conversely a max tree?
Yep. You can do a max tree, a max heap, which is just the opposite. And what's this heap? Min heap and max heap is the terminology specifically for this kind of tree. I believe there are heaps that are not trees. So this is just this particular application.
So should we try to figure out what heap is, or leave that?
Don't worry about that. I mean, you can kind of see it. It's like a pile of things where the smallest are on the or the largest are on the bottom, and it's like a heap of a pile. Exactly.
I know heap in like Australia means like a lot.
Okay.
That's what they say.
Yeah. I wish I could tell you the like deep history of min heaps. You know, and just to drive the point home, finding the minimum of a set, if you had all of these elements in an array, what would be your runtime, your time complexity to find the minimum of that set?
Maybe O of n.
Mm-hmm.
Big O of n. What's the time complexity to find the minimum here?
One.
Constant time. It's the simplest thing. It's just the top node. And yeah, so there's a kind of interesting property I'll say the operations on a min heap or a max heap are pretty interesting. If you want to insert a node to a min heap, what you do is, and I'm looking at my notes for this, you add a node to the bottom leftmost spot. So maintaining that the tree is complete. So let's say we wanted to add 3. So we add it here. I'm going to do this in green. So this is our new one. And then you bubble it up. You fix the tree. And you do that by swapping the new element that you've just added with its parent until the tree is a min heap again. So what we would do is we'd take that and we'd swap it with this. So now this is a 3, and this would be a 4. Do we have to do anything else?
No.
No.
What told you to string it off of what was before? Like it's just having open space left there?
Yep.
Okay.
Bottommost, leftmost spot.
I think because we wanted to maintain like the complete, we want to maintain the complete condition.
Right.
Mm-hmm.
And that's why I want to start with the left, but then also if you have an open on the right, then you go there first.
So if that had been, I feel like that makes it so there's a condition where like you could put one there and the number that it's bigger than is actually on the other tree, and then you like swap it and it looks good on that side, but it's not actually.
That doesn't matter.
Okay.
That doesn't matter. So you can have 13 and 9 or 9 and 13. And what's important is that it satisfies this property where
I guess what if you would put 10? Oh, I guess that would be
min heap. It's each node is smaller than its children. Node is smaller than its children.
Does that also mean that, by definition, is each, I guess, row smaller than all of the children in the next row, or could it be true that that like the one like on the row where there's 2 and 3, it could be like 2 and like 15, as long as the nodes that were 15 children were 17 and 18.
right.
Straight up. So this is 15. And this is 17 and what?
18.
18.
So
So is each of this node's child nodes smaller than, is this node smaller than its children?
Yes.
Is this node smaller than its children?
Yes.
This one?
Yes.
Yes.
No children? No children. Is this one smaller than its children?
Yes.
Yes.
No children.
That's
So if you do that, so really the min heap is only useful for the first
For the minimum.
the absolute.
Yep. So what if we wanted to add 0, the number 0 to this tree? Where would we add it?
It's gonna go on the right, like on the right side as well. So one is gonna be on the left side.
Well, before we do that,
Oh,
so the
sorry.
process of inserting, where do we insert it?
Oh.
13. Up to 13.
On 13.
To the left. Okay, so we've got 0 now. And then what do we do? Yeah, so we fix it, meaning we look, and if this is smaller than its parent, we switch them. So 0, 13,
And the 2.
so we switch these two to 0, and then one more time. Now the minimum is at the root.
So that, like you said, I guess as you're saying, if the more you do with this, everything that's not the minimum just becomes some set of data that's not really reasonable.
Not ordered.
That's a big.
Very specific use.
Yeah. And yet it still holds that you can always insert a node by putting it at the bottom leftmost spot, bubble it up, and that will fix the tree
Until it gets to the spot
where it needs to be. Yeah.
it's smaller than its kids.
Yep.
And it's smaller than its dad.
Smaller than its mom or dad. Yep.
So I guess linked list, I'm used to that being like, I guess unless it's doubly linked, any given node only knows one direction. I guess if you stick something at the bottom of this, is it aware of its parent, or is the parent aware of it, or how does that work? If we were to implement
Yeah,
this?
that depends on the data structure that you use. So you could, I don't want to switch to, well, I can just do it here. You could have a node data structure that has just the value, something, say the value is 5, and children is an array of, A and Z and F and, whatever those would be. There's nothing stopping you from saying parent equals,
Okay.
my parent.
Okay. I guess the next part of that was say, like, are there times where people set up where each node might reference like a few different types of data structures? So it's like this node, if you were looking at min-heap, the next one would be this, but if you're looking at a binary search tree, the next one would be this. So that at any given node, you can like take different paths to get results of data. Or is that like crazy?
I don't follow.
Like, so we have this node, or like this node has this value, and then here's some relational data about the stuff around it. Could you have it where you're like, this node has this value, and were you trying to complete a binary search tree, these would be the next ones. But were you trying to complete a min?
Oh,
Here.
interesting. So you have the min heap children
Right.
and min heap parent, but you could also have binary search tree children
Right.
Oh, okay.
and binary search tree parent.
So that if this was Facebook, we find this person, and now we have access to their search list and their minimum and all this other stuff without having to like recalculate it. We build the tree each time. I guess.
Mhm.
Okay.
Do we think this can work?
I mean, I don't recommend it for a friend, but
Well, I love that you brought this up. As far as I can tell, there's no reason you couldn't do this, and actually there's some reasons that you might want to, because again, nodes are just these like simple data structures that may have a value and then define the relationships between them and other nodes. And here, you're defining your relationship between yourself and other nodes in a min-heap context. Here you're doing the same thing in a binary search tree context, but the two don't have to mix. You still, the node still exists, and the relationships just change.
So it's like the node is part of two different trees.
Yeah.
You could just pick which one to use based on whether you're trying to find a minimum or whether you're trying to search.
Yeah. I was going to try to come up with some metaphor like in Dungeons and Dragons with my friends, I'm a like super wizard. And in Dungeons and Dragons with my other group of friends, I'm not. But I don't know enough about Dungeons and Dragons.
That is actually my life right now. I'm a bard in one campaign and I'm a shaman in another.
There you go. That's proof. This is proof.
Yep.
That's good. Yeah, so further study for you would be removal. There are actually, you know, for all of these trees, there are different operations that you want to check out. So you could check out how you remove the minimum. I want to make sure we get to depth-first searching and breadth-first searching. And so I'm just going to say that another thing that you might check out that is super interesting is a trie. And it's spelled kind of funny. It's T-R-I-E. And it's a tree that you can populate with the entire English language and use to find find all the words that end or that start with a particular prefix. So if you type like H-E-L, you know, you could quickly find all of the possible suffixes or ends to this word. So, you know, hell and hello and help. And
So this would be good for maybe search engine auto.
Yeah,
There's
exactly.
a search contacts algorithm that I think we're supposed to use that.
Yeah, so check out tries, T-R-I-E. So the thing that I want to make sure to get to, yeah. So a depth-first search. So you can do a depth-first search. So there's a depth-first search and there's a breadth-first search. And you can do these on trees or graphs, trees being a kind of graph. But I'm going to just use an example here of, so Danny and Miles and Sal, and it doesn't have to be a binary tree, so you can have over here Jack, and down here, let's say we have Phil. And here we have Fode, right? I would get everybody's name, but I'm going to stop there.
Oh, that's cool.
So, Fode's. Oh, well, let's put Jen. I mean, not everybody else. We get everybody else? Oh, Bob is in there. Okay, we'll add Bob too. I just put you down as bye. Bye, boy. Okay, so breadth-first search, depth-first search. Have you guys heard of these?
Yes.
Okay. Who wants to take a crack at describing a depth-first search?
I think that's the one that I understand. And you start at the head or root node, and you go all the way down the left side, and then you start coming back up. And for each one that has a right, you then go down that and then go all the way down its left side. So you're trying to evaluate basically everything on the left first.
You go full depth first,
and
then you go to
as
the.
as possible till you cover everything down there and then move your way back up.
Yeah. So say we were looking for Jen. Where's Jen? Walk me through the nodes that we would touch in that search.
We would go to Phil, and then because Phil doesn't have any children back up to Miles.
Okay, so Phil, here, we'll do Phil.
Wait, sorry, so it's you start from the root?
You go all the way down as far as you can.
Also, you start from there?
Yeah, I guess you look at the root, but you're like, how far down can I go to the left before you start evaluating?
Oh, so you don't go Danny, like, so you don't go Danny, Miles, Phil, you just go, okay, so since Danny the root, I'm gonna go like Phil, back up Miles?
Right, it would be like, does Danny have children? Yes. Let's evaluate how many children down we can go until we can know it's like we don't have any children. So what is Phil's value?
Yeah,
I question that all the time.
What is Phil's value? Phil, you're valuable to us.
Friend, a brother.
I think it's different than that.
Okay.
Let me say how. So DepthFirst Search, you would search and see Danny. Okay. You would search and see Miles. You would search and see Phil. And I'm putting a star just to indicate that we visited them. And then where would you go?
That's what I understood from your definition, which is like start from the root and then look up all the nodes on the left, all the way to the bottom, and then if no match, then you go up against the previous one, and then you go on the right side and then go left again.
Okay.
It could be
So-
that the root node is Jen, right?
So now
It
we
could
go to
be.
Sal.
So in that case, we have to check the root first, not the left.
Correct. Yep. Yeah. You may be thinking of prefix searching or prefix order, prefix traversal, and postfix traversal. No, I forget exactly what the terminology is.
You're trying to solve an algorithm problem,
Uh-huh.
and then never had any need to touch
All right.
it again.
All right, so we just checked Phil. Phil does not equal Jen. So we go back up here. Are there any other children of Miles? No. So we go back up here. Are there any other children of Danny? Yes. So we go and we visit Sal. You know what would make a lot more sense than stars is just writing the number, the order. So this was 1, 2, 3, 4. Where do we go next?
Left.
So isn't the first question that we ask when we get to Sal is, does Sal equal Jen?
Correct. Does Sal equal Jen? Never. So then we go left to Fode.
Right.
Fode does not equal Jen. We go left to Bai. Bai does not equal Jen. We go back up here. Does Fode have any other children? Okay, no. Does Sal have any other children?
Yes.
Yes. Does Jen equal Jen?
Yes.
Yes. So that would be the 7th, and then we win, and we stop.
And then so question. So when you went back, so the first time you went all the way down to Phil and then back to Danny, why did you go to Sal instead of Jack?
Sal instead of Jack. Just following the order of the nodes. So this would be represented in your data structure as like an array of children. Danny has a name Danny, and then children is an array, and the array would just be Miles, Sal, Jack, and that's just the order that they're in that array.
It's like you're picking left to right, but then if you were to also pick right to left, would that still be considered DepthFirst Search?
Yes. Yeah. There's no particular ordering in this case that matters. It would just be kind of odd to code to be like, go to index 0, then go to index 3, then go to index 2. It just makes sense to go index 0, index 1, index 2.
So when you say this properly, when you're at Danny, you would know if Jen is on the right or the left, right?
Nope. This is not a binary search tree or any kind of tree where we've defined specific properties. This is just a tree. It is a tree because it has a root node. It doesn't have any cycles, but besides that, it's just a tree.
So you write this as code for us. I believe you're saying it would be a multi-dimensional array.
Yeah, it's funny you mention writing this as code for you. And folks that are on Zoom will not be able to see this. But okay, so this is pseudocode, and more than pseudocode, it's actually bad pseudocode. It's kind of crappy Pythonic JavaScript pseudocode. But here's the basic algorithm. DepthFirst Search, we'll call this DepthFirst Search, you start with a node. This would be root. If that node is null, then you just return it. But it's not null in this case. So you visit that node. We visited that node first, Danny. We said, is Danny equal to Jen? So this is where you would do the actual check, the kind of comparison. Like, is this the thing that we're looking for? You mark this as visited. And this is relevant only when you have a graph with cycles, where you might actually come back around to the same thing. In a tree, not necessary. Then for each node, which I'm calling $sign subnode.
I'm sorry, you said in a tree that's not necessary?
It's not necessary to mark it as visited.
Isn't this a tree?
Yes. Yeah, so this line in a tree is not necessary. In a graph, it is, and that's why it's in there. Because the algorithm that you're doing says, like, go down this route, go down this route, go down this route, but those routes are never going to end back at the same place, and you're never going to come back to that spot again.
DepthFirst Search and BreadthFirst Search trees and
Yes. Yep. So for each, I want to tell people to quiet down, but I won't. For each node, which we're calling subnode, in the adjacency list, so this could be adjacent or it could be children, that's what we've been calling it.
Yep.
If that subnode is visited, then if it's not visited, so again, this doesn't matter in a tree, it does in a graph, search that. So we'll do a depth first search of that subnode. So this is recursive. This is recursion, where you do this, you run this here, and then you look at the first child and you run it on that child, and then it ends up running it on its child, and then of course it goes to Sal. So I want to make sure to at least touch on BreadthFirst Search before we wrap up. So if that's DepthFirst Search, you are going to the greatest depth first. BreadthFirst Search works a little bit differently.
Can I ask a question for you?
Yeah.
So because you said that in a tree, you don't have to check if the node is visited because it's only going like down the path going one way. But with this example, we had to go circle back, right? So this is a graph, not a tree. Is that correct?
This is a tree.
So,
Trust me on this one.
okay.
I encourage you to write a DepthFirst Search algorithm. Make yourself a kind of simple tree, write a DepthFirst Search algorithm, and you'll see how you visit something, and then there's not a way in your recursive algorithm that you will actually visit it again. So BreadthFirst Search has a kind of interesting algorithm. And here's the key. When you're going into an interview and you think BreadthFirst Search is coming up, or they say, hey, please implement a BreadthFirst Search, which would be a kind of mean thing to ask, but it happens.
I'll throw something.
Here's
You have a better BreadthFirst Search. Right.
So the thing to remember is that a BreadthFirst Search needs a queue. It must have a queue. I don't know of a way to implement it without a queue. And once you've got the queue, the rest kind of flows from there. So I'm going to just kind of burn through this. You guys stop me if you think I've made a mistake. So we've got a queue. We mark this root node as marked or visited. But again, in this case, because it's a tree, that's not going to matter. It would matter in a graph because you don't want to visit a thing multiple times. And then we put this on the queue. So here's our queue. So we enqueue Danny. And then the algorithm goes like this. It just loops here. While the queue is not empty, and it's not empty, we take a node off the queue. So we're going to pop Danny back off the queue. Danny is down here for our consideration. We visit Danny. So this is where we ask, is Danny equal to Jen? Say we're doing the purpose of our BreadthFirst search again is to find Jen. Is Danny equal to Jen? No. So we don't return, we don't stop the search. So then for each node in the adjacent nodes to Danny, so again, this could be children, if they're not already visited, we mark them as visited. And again, that doesn't matter if it's a tree. And then we put them on the queue. So for each of the children here, we put them on the queue. So Miles goes on, and then Sal, and then Jack. So Danny was first, and we'll see what happens next. So we repeat this. We take the first thing off the queue, because again, a queue is first in, first out. So we take Miles off the queue. Miles is down here for our consideration. We say, is Miles Jen? Nope, not Jen. So we've now visited Miles. What's that? And then, so we visit him, and now for each of Miles' children, we add them to the queue. So Phil, let's put on the queue. So now, again, we take Sal, we pop Sal off the queue, and we're considering Sal. Is Sal equal to Jen? Nope. So Sal gets visited third. So you see how this is different from BreadthFirst Search, or DepthFirst Search. Okay? And then we add Sal's children to the queue. And so I'm going to move this over just for readability. Jack, Phil, and now Sal's children are Fode and Jen. Okay, what's next?
We DQ Jack.
DQ Jack. Is Jack Jen?
No.
No. So we've visited Jack. Jack is not Jen, but we add all of Jack's children to the queue. There are no children, so we're good. We DQ Phil. Phil, is Phil equal to Jen? No. So 5. And we add all of Phil's children to the queue. No children. Fode comes off the queue. Is Fode equal to Jen? No, but we visited.
When we add by,
Now we would add by, our nickname for Bob, and continue on. We pop Jen off the queue. Is Jen equal to Jen?
correct.
Yes. So we can now return out of our algorithm and not search anymore because we found Jen. 7. Ding, 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 ding. Make sense?
Yeah.
Do you see why the queue is necessary?
Mm-hmm.
Because you have to add the children to be searched after everything else that you've already put in the queue to search. Otherwise, you might get some sort of like DepthFirst search. This is another one. Take my word for it. Implement this. Make yourself a little graph. Implement this and do an actual search through it. And I guarantee you, by the time you're done writing the code for BreadthFirst Search, you'll see why.
So I almost feel like visually it's like depth, breadth.
Yeah.
Right? Because you're going across the children of each node.
Yep. Yeah. And it gets pretty interesting in a graph, especially a graph with cycles and things like that. That's where the visited or marked property matters, because a DepthFirst Search shoots out from the center, and a BreadthFirst Search just kind of grows out to each progressive depth out, or each progressive layer out.
If you didn't mark the visitor and try to do a DepthFirst Search, you could get stuck in a loop or something.
Yes. Yep.
That'd be bad.
What are each of these searches used for? Like, why do we need to know about a DepthFirst or BreadthFirst?
I so wish I had time to answer that. I do need to go to a meeting. So if you're trying to find, if you have a graph and you're trying to find the shortest path, BreadthFirst Search, like if you have 2 points on a graph and you want to find a path between them, BreadthFirst Search will actually do that if you do a BreadthFirst search from this one and from the other one. But there is a better shortest path algorithm called Dijkstra's algorithm. That's a cool one to check out. Highly recommend. It's like DJIKST, something like that.
Is it the one Uber uses?
I don't know. It might very well be.
There's also A-star algorithm.
Oh, there are so many. Yeah, so many really interesting algorithms. You can think about, so I think the kind of simple answer to your question is, we end up with data structured in graphs or trees quite a bit in the real world. You've got to search them somehow. DepthFirst Search and BreadthFirst Search are 2 ways to do it, and each has its own advantages, which you can kind of see. Like if, if Jen were here, you could see the advantage of a BreadthFirst search. If this tree were 1,000, had a depth of 1,000, there were 1,000 rows in this tree, which would be the better algorithm if we knew Jen was, within the first couple rows of depth. BreadthFirst. And in other applications, DepthFirst is useful. So that would be if there is a kind of bounded depth, you're not going to just go on forever. I mean, you can imagine if you took, so every city in the United States is a node, every road between them is an edge, and you were trying to find the path from New Haven, Connecticut to Oakland, California. A DepthFirst search would be really bad, right? Because you might first go up into Maine, and then you might go, to New York, and then you might go to Washington D.C., and then you might go to Florida. You might traverse, as far as roads go, before you even started moving in the direction of Oakland, California. And I don't know what the ideal algorithm would be to do that. It might be this kind of dual BreadthFirst search. And then, of course, there are tons of optimizations that you can do. So there's no way that Google is doing a dual BreadthFirst search from those 2 cities through all of the intervening roads every time you make a query. So they've got some caching and some kind of heuristics that make their algorithms faster. This is why I love it. It's just so interesting. I've got to go, but thanks, everybody.